Okay, so the characteristic foliation is a very particular example of a foliation, and it lives, well, in this talk it will live on a smooth hypersurface in a holomorphic symplectic manifold. So first I will tell you what is a holomorphic symplectic manifold. So it's abbreviated to HSM. This just means that X is compact Kähler, and the space of holomorphic two forms. And X carries a holomorphic symplectic form. Symplectic means, of course, nowhere degenerate. So let me put it as X sigma. Well, I will mostly work with irreducible holomorphic symplectic manifolds, which are abbreviated to IHSM. Well, this means that this symplectic form is essentially unique, and also that X is simply connected. Simply connected. And H20 of X is C times sigma. Okay? There is a theorem by Bogomolov which says that every HSM is a product, well, up to a finite covering, is a product of a torus and several IHSM. So if X is an HSM, then a finite covering X tilde is a torus times, well, a product of, let's say, yi, where yi are IHSM. An example of an irreducible holomorphic symplectic manifold is a K3 surface, or more generally, Hilbert schemes of points on a K3 surface. Hilp n of X are, Hilp n of S are IHSM. Okay, so let's take a hypersurface in a holomorphic symplectic manifold. And then questions? Other questions? And then the restriction of sigma to D acquires a one-dimensional kernel. Sigma to D has one-dimensional kernel. So this is called the characteristic foliation. Of course, the the characteristic foliation. Well, characteristic foliation. Well, it's really a foliation because, well, for rank 1 things we don't need to check the integrability condition, and this is without singularities. So it's a regular foliation. For example, if your D is uniroot, that's covered by rational curves. If D is uniroot, Well, and of course you have examples of such uniruled divisors on holomorphic symplectic manifolds. You can consider, for instance, the exceptional set of the Hilbert-Chow morphism, right? Exceptional divisor on the Hilbert square. Then the leaves of our characteristic foliations are just foliation are just rational curves. This is easy to see in general because a uniruled variety has what you call a rational quotient. This is a rational fibration such that the fiber through a general point is all you can reach out of this point by chains of rational curves. So fibers are what is called rationally connected varieties, and these rationally connected varieties don't carry any holomorphic forms, so our sigma must be a pullback of a form on Q. So this means, in particular, that the fibers of this rational quotient are one-dimensional, and well, these are rational curves, of course, and sigma vanishes along those rational curves. Well, the kernel of sigma is exactly along those rational curves. So this is, let's say, R star of some, I don't know, omega. Okay. So one may ask the question: does it happen often that the leaves of well, that our foliation is algebraically integrable? Well, the question is f often algebraically integral. And the first people who considered this question were Huang and Vivek. In, I think, 08. And they proved that if D was of general type, then it was never the case. If G is of general type, and well, not a curve in a surface, of course, we don't care about this degenerate case, and the dimension of X is strictly greater than 2, then F is not algebraically integrable. So, of course, you want to know, I mean, if it's uniruled, it's algebraically integrable. If it's of general type, it's not. It's natural to ask what is in between. And we answered this question with Frédéric Campana in about 14, I think. Or 15, maybe 15. I don't remember. So we classified the situations when this is algebraically integrable. Oh, sorry, I forgot to mention that in both theorems by Huang and Vivek and by myself and Campana, X is projective. So suppose that D is not uniruled, then if f is algebraically integrable, well, f is algebraically integrable, if and only if up to a phi, well, not if and only if, because it depends on your form, of course. Then if f is algebraically integrable, x up to a finite étale covering, is a product with a surface, and G is a product with a curve. So this is a holomorphic symplectic surface. This is a curve. And Y is a holomorphic symplectic manifold. Well, it's not always true that the form sigma needs to be a product, right? So I did not write if and only if here. Because, of course, I mean, it depends on which symplectic form you take. There are many symplectic forms on such a product. So for some of them, of course, the characteristic foliation will not be algebraic. In particular, if X is irreducible, then the foliation, the characteristic foliation is algebraically integrable if and only if it's uniruled. So in particular, if X is IHSM, then F algebraically integrable if and only if G is uniruled. Well, provided, of course, that X is not a surface. But this case is trivial. OK. So how did we prove this? I just will give you a brief idea. The key point is to prove, well, so you have this D, and you suppose F is algebraic. So D is fiber-chain curves, well, of genus, of positive genus, because we suppose that G is not uniruled. And in fact, the base carries a holomorphic symplectic form. I mean, this restriction of sigma to D descends to the base. The base is mildly singular, but only mildly. It's not very, these singularities are quotient singularities. It's not very serious. So idea of proof is that you have this D. So if G is fibered over B in curves of genus, of positive genus, well, you know that on B, well, sigma restricted to G is a pullback of some toy, right? Well, toy is a holomorphic symplectic form on B. So B is a holomorphic symplectic variety. It has a trivial canonical bundle, for instance. And families of curves over such varieties tend to be isotrivial. Well, show that this family of curves is isotrivial. Well, if you know something about moduli spaces of curves and other, say, canonically polarized varieties or varieties with trivial canonical class, this statement is in fact very natural. So I will not comment.
What is really the reason of isotropy?
What is what?
Reason. Why it is isotropy?
Positivity of relative canonical bundle. Well, we can talk about this later. I only have when you know it's isotrivial, then of course you know a lot about this D. Well, I mean it's a product after a finite covering. So you know, for instance, that the Kodaira dimension of D is 0 if G is 1, and 1 if G is strictly positive, strictly greater than 1, sorry. Well, you know that KD is NF, you know that the abundance conjecture is true. Well, on irreducible holomorphic symplectic varieties, on irreducible holomorphic symplectic varieties, you know, in fact, that this Kodaira dimension can take very few values. Well, we know that the Kodaira dimension of, well, not of D, but of OX on D is either 2n, well, the full one, if D square is positive, well, D and D square, I mean, Beauville-Bogomolov square, but I did not mention it, so let's take it D2n. Well, and if D2n is 0 and, well, minus infinity otherwise. So in fact, I mean, the Kodaira dimension of D is this minus 1, right? The canonical class of D is OG restricted to D. You see that this is possible only if X is a fourfold. Kodaira dimension of D is 1, and it's fibered in curves of genus strictly greater than 1, and you rule this case out. So Kodaira dimension of G is just the Kodaira dimension of OXG minus 1, and you just rule this remaining case out, considering explicitly the Itaka fibration. Well, you see that, in fact, the fibers of this Itaka fibration are Lagrangian subvarieties. Because they are equivalent to D square as cycles. Well, maybe I should really, at this point, I should say something about the Beauville-Bogomolov form, because this is a non-trivial point. Well, Y equivalent to D square as cycles implies Lagrangian. Well, maybe I was going to talk about it later, but maybe I should do this right now. So the Beauville-Bogomolov form on an irreducible holomorphic symplectic manifold, you have a quadratic form Q on H2. The Beauville-Bogomolov form And this is a kind of an nth root of the intersection form. Q of g to the power n is proportional. Well, this is quadratic. This is proportional to the self-intersection. Well, you can define it like this as an nth root of the intersection form. But of course, it's only up to sign, and there is an explicit definition with integration and so on. Or let's say Q d1, d2. If you have two, let's say, effective divisors up to a constant, it's the integral over their intersection of sigma sigma bar to the appropriate power. What is the power? N minus 1 or n minus 2? N minus 1, right? Hopefully. So you see, if you are equivalent to d square as a cycle, then the Bogomolov form of yours is 0, and so sigma must vanish on such surfaces. Yes, fibers are Lagrangian. So the characteristic foliation is tangent to those fibers. This is why it's important. They are Lagrangian. So F is tangent to fibers. But on the other hand, it's Ithaka fibration. So the fibers have Kodaira dimension 0. These are minimal surfaces of Kodaira dimension 0. And they just cannot be fibered in curves of genus greater than 1. But they cannot be fibered in curves of genus greater than 1. Well, I am going into some detail here because this kind of argument, in fact, will be used a couple of times in this story. But the story I want to tell is more recent. Well, now, OK, we know it's almost never algebraic, this characteristic foliation. In particular, on an irreducible holomorphic symplectic manifold, it's algebraic only if our divisor is uniruled. But you can ask, what is the dimension of the Zariski closure of the leaves of such a foliation? So question. So let X be IHSM. Okay, irreducible holomorphic symplectic manifold. So symplectic form is essentially unique, and you have this wonderful Bogomolov form, which is really very useful. What is the dimension of Zariski closure of a general leaf? Well, what do I mean by a general leaf? If you take those Zariski closures of leaves, they fit into countably many families. You have a kind of invariant Hilbert scheme. You consider the Hilbert scheme of all subvarieties invariant by foliations, by this foliation, and this has countably many components. So some of those components are not dominant, and I say these leaves are not general, and one of them is dominant, and I say this is my general leaves. So I hope it's more or less clear. So general, let's say, through a point outside of a countable union of closed subvarieties. And where this countable union comes from, this is this invariant Hilbert scheme. Okay, yes, this is outside of a countable union of proper subvarieties, which are non-dominating components of the invariant Hilbert scheme, F invariant Hilbert. Okay? And we answered this question with a pupil of mine, well, a former pupil of mine. She was an undergraduate as a pupil of mine. Now she is doing her PhD with somebody else. So a theorem joined with Guseva of 16. We answered this question in dimension 4. If the dimension of X is 4, and X is not necessarily projective. So suppose that G is not unirode. Well, the characteristic foliation be not algebraic. Not algebraic. But the dimension of the Zariski closure of a general leaf, well, let's denote it as L bar Zar. I don't know. The dimension of this L bar Zar, so L from leaf, bar from closure, Zar from Zariski, is 2. So then we have a rational fibration of our G by such Zariski closures over a curve. Rational fibration, well, meromorphic fibration, if we are in the compact Keller case, by such Zariski closures. So let's see, suppose. So we suppose all this, then this phi is regular, and this is a fibration in Lagrangian tori. Phi is regular, the fibration is in Lagrangian tori, and in fact it extends to a Lagrangian fibration on X. Then phi is regular, fibers are Lagrangian. Right? Well, abelian surfaces. In fact, they are projective even if X is not. It's not difficult to see. And phi extends to P, well, to P from X to B. Oh, a Lagrangian fibration. Well, only rational, I think, a priori. Phi is regular, but this P is an almost holomorphic map. You make a flope, it becomes holomorphic, but a priori, it's only almost holomorphic. Okay, so what is the idea of this proof? In fact, our proof was, well, it was valid once also in the compact Keller case, and it went by classification. It went by classification. Of foliations of surfaces. You see, it turns out that there are not so many surfaces which admit everywhere regular foliations. And the fact that the whole story comes from holomorphic symplectic geometry, it tells you something about invariance of those foliations. Well, first you prove that phi is regular. Then you have, of course, this sigma, which induces what? It induces what? This is, well, let S be a general fiber. Then you have n of f restricted to S. The normal bundle goes to the quotient by the kernel, or is it the conormal bundle? No, I think it's a normal bundle. Yes, and then it goes to n. Well, the normal bundle of S and G. You have an exact sequence like this, using that your holomorphic symplectic form gives you some dualities. So this has trivial determinant. This has trivial determinant. So this has also trivial determinant. And then, well, recover. What do you recover? Recover that the determinant of f, not the determinant of f, but n f restricted to S is trivial. You recover that C2f of S is 0, and so on. So, for instance, you see that S is not of general type. And then you, well, essentially you arrive to the alternative, either S is a torus and then we win, or S is an elliptic surface, a properly elliptic surface of Kodaira dimension 1. And then it's a bit painful to rule this out, but I will tell you it's much easier in the case when our variety is actually algebraic. So I arrive at, well, either S is properly elliptic, and then, well, work, or S is a torus, and then we win. Because, in fact, there is a result which says that if you have any Lagrangian torus on an irreducible holomorphic symplectic manifold, it is a fiber of a Lagrangian fibration. Well, in this 4-dimensional case, you don't even need this result. I mean, the result is easy in dimension 4, and actually is due to myself. But in general, it's due to Huang and Weiss. Any Lagrangian torus on X is a fiber of a Lagrangian fibration. Well, now this part of ruling out the elliptic surface becomes not necessary if our manifold is projective. because then we have this wonderful Boville-Bogomolov form, and we have minimal model theory. I mean, Boville-Bogomolov form we always have, of course, but use MMP. This was a remark suggested by Campana. What you do in the projective case, you reason in function of this Bogomolov form, Boville-Bogomolov form. So you look at Q of D. Well, maybe I'll continue in yellow. Look at Q of D. So well, it can be negative. Then it's known that D is uniroot by Sébastien Buxom, je pense. So this is the case which we know. Then Q of D might be positive. Then we know that D is of general type. But then S is also of general type. S is a surface in which D is fibered, so S is of general type. And then we know that C2 cannot be 0. Or Q of G is 0. And then we use MMP, well, which says that D becomes nef after a flow. And then you have this Ithaca fibration. Well, then you have Ithaca fibration. Like in the argument I was sketching you before, like in the last argument. So the fibration, well, in fact, this should coincide with phi. And so we conclude that S is a torus. I mean, we rule out this properly elliptic case just immediately. I mean, maybe S is a K3, but then K3s cannot be fibered in curves, well, of higher genus. Well, you know what I mean. No, K3s don't have C2 equal to 0. I mean, you use some classification, but now something which everybody knows to arrive to the case when S is a torus. So, okay, one might ask a question. What happens in general? Is it true that you have this kind of trichotomy? Is it true that you have this kind of trichotomy? Well, for X projective, maybe it would be too bold to hope to prove this for any X. So question. So X projective, IHSM, irreducible holomorphic symplectic manifold, as always, G a smooth hypersurface. So is it true? The following alternative hold. So either F is algebraically integrable, basically meaning that Q of G is negative, Or there is a Lagrangian fibration. Lagrangian fibration, and G is a pullback of some divisor, right? Of some H on B, and leaves of F, well, closure, Zariski closure, are algebraic tori, Lagrangian tori, well, are fibers of P. Well, or, well, this corresponds, of course, to the case Q of G is 0, or Q of G is positive, and the closures of leaves are large. I don't know whether one can dare to say Zariski dense. I don't know. Honestly, I have no clue. Maybe Georgia or some other people who know more about foliations can tell whether this is too bold or have any chance to function. Leaves are large. So, of course, this case is mysterious. This case is mysterious. This case is done. This case is hard. Let's look at this case, the intermediate one. In fact, there is a well-known conjecture in holomorphic symplectic geometry, which is called Lagrangian Conjecture. It is a version of abundance conjecture for, well, in usual birational geometry. So what it claims, this Lagrangian conjecture, is that essentially if you have G, which is maybe in the closure of the movable cone, well, if you have a G, sufficiently good G, with 0 square, then it gives you already a Lagrangian fibration. Then it's semi-ample. Well, in any case, you can conjecture that if G is F, then it's semi-ample in this case. Lagrangian conjecture. So if G is F and Q of G is 0, then G is semi-ample. So there exists such a Lagrangian fibration, which is given by the sections of an appropriate power of G. By sections of some power O of G to the power n. Okay? So if this G is not necessarily an F, you can hope to flop your manifold in such a way that it becomes an F, and you still have this Lagrangian fibration, only rational one. This is, of course, a conjecture. But it's not completely, well, it's not something completely fantasist. I mean, it's known for deformations of Hilbert scheme of K3 surfaces. So known for Hilb n of K3 and their deformations. So, well, an easier version of this question is as follows. Suppose you already have this Lagrangian fibration. And suppose that G is already the inverse image of something on the base. can you prove, well, of course, the leaves of this characteristic foliation are contained in the fibers. I mean, the kernels are, of course, contained in isotropic subvarieties. But can you prove that they fill the whole fibers? Can you prove that the Zariski closure of a general leaf of F is the whole fiber of P and not just a proper subtorus? Okay? So easier question. So let's say question, modular Lagrangian conjecture. So suppose, I think in this case B is actually going to be Pn. Not quite sure, but in any case, the theorem I am going to explain to you is, supposes that B is Pn, but it is proved by Huang that B is Pn whenever smooth. Okay, so suppose that Lagrangian conjecture is true. So one has P from X to Pn, let's see. Was it P or was it other thing? Yes, P. And D is the inverse image of something, some divisor on B. Well, can one show? Then it is obvious that leaves of F are contained in the fibers of P. Okay? Is it true that, in fact, the Zariski closure is the whole fiber? A student who began his thesis with me just proved that this is indeed true. So is it true that so a theorem by Renat Abugaliev. Well, yes. He really has to assume, well, he really has to assume that the base is Pn. But the base is Pn, amounts to say that it is smooth. Remark. So maybe I should erase this Pn here. I mean, in general, I guess you can have some quotient singularities, or, well, in dimension 4, it seems you don't. So maybe I put a question mark here. Remark, well, Huang proved that if B is smooth, then B is Pn. So, how does he prove it? How does he prove it? The idea is to look at the rank. So idea. So let, well, this is a bad notation. How can I denote it? Maybe I will still denote it by S. It's not a surface anymore, but otherwise I would not like to confuse with this round F. Let S be a fiber of P. So this is a Lagrangian torus of dimension n, an abelian variety, in fact. Then is known. It is known that the rank of the image of the restriction of the second cohomologies of X to the second cohomologies of F is 1. This is a remark by Ogiso, but it follows very, very quickly from two results, one by Voisin and another by Matsushita. Yes, so he does topology. Well, this means, of course, that the rank is 1. This means that the action of P1 of Pn minus discriminant, well, the discriminant, well, set of critical values, on H2 H2F has only one-dimensional invariant subspace. Well, you see there is this Deligne invariant cycle theorem, which says that it's the same. Cycles which are invariant under the action of monodromy are cycles which are restriction from the ambient variety X, right? Now, if H, this divisor on Pn, is generic, then of course P1 of H minus delta intersection with H surjects onto P1 of this. If H is generic, then P1 of H minus P, H minus H intersection with delta surjects onto P1 of Pn minus delta. So the action of the monodromy of H does not have many invariants either. So in fact, here we can replace X by G. So meaning the rank of the restriction of H2 GQ to the H2 SQ is also 1. But it should be more, because of course there is an obvious invariant cycle which is the restriction of the ample divisor. But if your characteristic foliation is somehow degenerate, if it gives you fibrations, well, fibration in tori on each fiber, then of course you will have another invariant cycle. So if the characteristic foliation is not totally transcendental, I think this was how Carolina called it. Totally, no. Well, if no, this is another notion, of course. If the leaves of F close to proper subtori, this is impossible. I mean, your G is going to be fibered over something, and the inverse image of an ample divisor on this something will give you another invariant cycle. Okay, so, well, the only problem in this argument is that H is generic, because, in fact, this is not equivalent to P1 of P minus 1 of H being smooth. No, so you have to sort of, well, I mean, you can have, for instance, if you're a delta, there are examples in which, say, delta has a cusp, and if H passes through the cusp, but is not really tangent to the cusp, then the pi1 of this guy is smooth. Whereas you don't have necessarily this surjectivity. But you can find an easy way around this. You can say that the inclusion of the fiber into a generic G and a smooth but non-generic G are homotopy equivalent. So you can repair this by saying that the inclusion of the fiber into a generic G and the inclusion of the fiber into a smooth non-generic G are homotopy equivalent. So this is the argument used to answer this easier question. But of course, the general, more difficult question still remains, what happens when Q of G is positive? Is it true that the leaves are necessarily large, and what means large? So thank you for your attention.